Hello, I'm Michael Tsirkin. I work at Red Hat as a distinguished engineer, and I'm a chair of the Virtio Technical Committee. And today I'm going to talk about the work we are doing in Virtio for the benefit of hardware Virtio implementations. And I think Virtio is kind of unusual in that it has been defined as a software interface, first of all, and hardware came afterwards. So we have hardware emulating software in a sense. I plan to describe some challenges that surface when you try to do it like this. And hopefully this is going to be interesting for people interested in both software and hardware. So I like starting with this slide because it just keeps growing year to year. This just shows all types of the devices for which we have a detailed description included in the Virtio specification. This by now is a huge specification. Just since the last year, we have included memory device, IMMU device, and sound device. And lots more are works in progress. So I guess the point I'd like to make here is that it's a very popular standard. And there exists around it a strong ecosystem, it's a large amount of existing devices. Most of these devices started out with a pure software implementation. And into the scene began to enter hardware implementations of Virtio. So it all began with the quest for performance, where a cloud vendor, for example, would say, well, right now I'm burning up host CPU cycles, moving packets, for example, between a Virtio device and a host NIC. How about we teach the NIC to talk Virtio directly instead? Sounds reasonable, doesn't it? And naturally, the NIC hardware would then be built to provide the features that existing guests use, since that's the software people want to speed up, right? In response, we on the Virtio side of things noticed this trend. And we thought, okay, so that's great, but isn't there anything we can do to make hardware work better? And we'll put it in the spec, we'll build it into software, and then with time, after the software is widely deployed, it will be worth it for hardware to target these software extensions. Of course, we don't do it in a vacuum. We have discussed these extensions with hardware vendors, so they make sense for them. And these extensions is what this presentation is about. So the reason hardware Virtio offload work at all is because Virtio devices actually pretend to be PCI devices for the virtual machine. And here I run the ls PCI command within the VM, and its output lists a bunch of PCI devices, among them a Virtio device. So if you implement a device that looks just like this, then existing drivers within VMs will bind and will work with your device. And that's a lot of software that can suddenly use your hardware without modification. Now, if you look at the specification of any Virtio device, there are usually two parts to it. And one part is device configuration. This is a control path interface used for initialization and things like that. But during data path operation, driver manipulates data in Virtqueues. These reside in guest RAM and accessed by device using direct memory access. Now, since Virtio hardware is primarily motivated by performance, then let's first of all talk about the data path. That is the Virtqueues. So this is the original Virtqueue format. It's called the split Virtqueue, and it was designed with software in mind. it is kind of hard to use efficiently from hardware. And this slide tries to show why. Without going too much detail, there's a Virtio card at the bottom, and the red arrows are PCI Express transactions that need to happen for the device to do something for the driver. I think even without knowing too much about it, you can see that there are lots of round trips from the device to main memory. All of these need to happen in order. Result of one read is necessary to initiate the second one. And each of these increases the latency of the device as observed by the driver. So the latest Virtio specification already made a first step towards improving this latency by introducing a packed ring Virtqueue. And that one simply consists of a ring of descriptors, where each descriptor includes a physical address and a length. They also include an identifier, which allows supporting out-of-order completions. We're going to talk about this a little later. There's a flags field, which marks a descriptor as available or used. And that's pretty much it. Now, to process some descriptors, device first reads the flags field to verify that the descriptor is valid. If it is, descriptor itself is read and processed, and afterwards, device writes into the flags field to mark the descriptor as used. Now, I think it's kind of obvious that less transactions are necessary here than with a split ring. In fact, on some platforms, read granularity is bigger than the descriptor size, and this removes the need for a separate read of the flags field. So it can be read with the rest of the descriptor atomically. However, this is not guaranteed by the PCI Express spec, and these platforms are generally not so easy to detect. For this reason, the Virtio spec now also includes a way to remove this extra read in a portable way. Specifically, devices can request that the offset of the last available descriptor is sent to them by the driver whenever the driver notifies the device that new buffers are available. And using that, we end up with a single read and two writes being sufficient to process a descriptor. That's way better than the split ring, just from the latency, from the transaction count point of view. But this is not the only optimization included in the Virtio spec. Here's another one. So it turns out it's pretty common for devices to use descriptors in the same order in which they were made available. For example, this is usually the case for the transmit ring of the Virtio network device. And that's because reordering packets by a network device is generally frowned upon. So in this case, device and driver can negotiate a feature which allows device to signal use of a batch of multiple buffers by only writing out the last descriptor in the batch. And this reduces the transaction count and the overhead on the PCI Express even further. A simple basic variant of this feature that I have described right now is already included in the released version of the Virtio specification, but that turned out to be somewhat limited. So to understand the limitation specifically, let me take a step back and talk about page faults first. Page faults, good or bad? There's an argument that goes something like this. Page faults slow things down. Now, hardware Virtio is all about performance. Therefore, hardware Virtio devices do not need page fault support. But I am not sure I agree. And let me start with an example. A Virtio hardware device might support thousands of virtual functions. Each one can be assigned to a virtual machine. So it might be practical if you have thousands of VMs to give each virtual machine a virtual function. However, it is not really practical to put memory of thousands of virtual machines on a single NUMA node, the one closest to the device. So what we do want is to put the most used memory of the most active virtual machines on this NUMA node. And one way to do it, to detect this most used memory of the most active virtual machines, would be in exactly the same way it's done for process memory. Device access to a page is blocked, and next access will cause a fault that we can detect and handle by moving the page closer to the device. With enough time, the result will adjust the workload and perform better than the static partitioning. I hope that's a good example that shows how page faults can actually be good for performance. But another argument revolves around the practicality of implementing the page faults efficiently. There are two main issues that I'm aware of. The first has to do with the fact that the PRI, the page request interface, which includes support for page faults from devices, is still not well supported on all current systems. Well, to address this problem, for now, devices can detect and report page faults to the host in a device-specific way. For example, through the physical function of the device. If the device has an on-device IMMU, detecting page faults is probably easier. Another problem that is often mentioned in this context is device stalls. Now, stalls are only a problem for some devices, such as the receive queue of the Virtio network device, which get lots of data from the outside world. Let's see, for example, why it isn't a big problem from the transmit ring of the Virtio network device. Well, at the bottom of the slide, you see a ring with a bunch of packets. Now, as long as ring is stalled, then the packets just stay in guest memory. Meanwhile, more packets can be queued in guest memory. With queues that are deep enough, no packets need to be lost. By comparison, let's see what the problem is for the receive ring. To the right here, you see packet number 1 incoming to the device. Now, driver has prepared multiple buffers in the receive ring. However, translating the first buffer immediately caused a page fault at the IMMU. Processing now stalls until the first buffer becomes available. Meanwhile, more packets arrive at the device. Since the ring is stalled, they are not stored in the buffers prepared for them by the driver. Eventually, the packets will overflow the device memory and cause packet drops. Turns out, however, that Virtio ring rules actually allow devices to fix this problem. The rule that I'm talking about is that devices can use buffers in an order that's different from that in which they were made available to them by the driver. And this capability is normally not used by networking devices. It's used by storage devices, such as Virtio block, for example. And we can utilize this capability to prevent stalls. After detecting a fault on a buffer, device can try storing the first packet using the next available buffer, and then the next packet using the buffer after that. In this picture, the fault at the first buffer got resolved after processing 4 packets. The 5th packet is now stored in the first buffer, and then we can proceed as usual. Note that buffers are reported to driver out of order in which they were made available, but in order with respect to incoming packets. So packets are not reordered from driver's point of view. That's great. However, handling a page fault like this doesn't coexist with the existing in-order optimization that I described previously, because that optimization disallowed used buffer reordering. For this reason, the Virtio Technical Committee is currently discussing an extension that allows both page fault handling and in-order optimization to coexist. Specifically, a new per descriptor flag is defined. It is only set when all previous outstanding buffers have been processed. Now, a device is only allowed to skip writing used descriptors if the flag is set and all previous outstanding buffers have been processed in order. Now, as long as there are page faults and buffers are used out of order, the flag is clear, and therefore all descriptors are written out by device. When things stabilize and there are no more page faults, then the flag is finally set, and the device can skip writing out some descriptors, improving performance. Let me try to advocate for page fault support in hardware some more. Well, page faults enable memory over commit, which is very popular among cloud vendors. For example, the hierarchical hypervisor seems to focus on overcommit as a very important feature. Now, a device with a large number of virtual functions should be able to support a virtual function per virtual machine. And if this can be made not to conflict with memory over commit, this hypervisor are likely to use this. Again, same can be said for transparent huge pages. These work by moving pages around, which in turn can only work if we can make some pages non-present, move them around, and make the pages present again. During this time, hardware can trigger faults. Again, the host could only be temporarily overcommitted, with user actually expecting performance to pick up once some memory becomes free. Post-copy live migration is another useful feature that needs page faults. Let's talk about how it works generally. Just shortly, a virtual machine is simply started on the destination, even though at least some of its memory has not been migrated there yet. Now, when guest accesses the missing memory, a page fault triggers. This is reported to QEMU using a user fault FD mechanism. And QEMU then fetches the page from source and restarts the guest. Now, this has multiple advantages. First, the virtual machine can start at destination sooner, freeing up source CPU. Even if guest accesses a lot of memory, it will still make progress and eventually migrate. That's unlike pre-copy, which sometimes suffers from leave locks from busy guests. Virtual machine memory and destination is not write protected. Once enough memory has been migrated, then no faults need to trigger. So that's nice. But it doesn't work with a hardware device. Why? Simply put, at the moment, hardware will try to pin all guest memory. At this point, it will just block on the destination until migration is complete. And this is not the destination of live migration. And here's how hardware page faults would fix this. When hardware accesses a missing page, a fault triggers. Page is then fetched from source, and device is notified to retry the access. Note that at least at the moment, the page request interface support on Linux doesn't support user fault FD. One way to address that would be to again use a device-specific way to trigger user fault FD on a hardware page fault. Note also that again, if there's locality to device accesses, the first access will cause a fault, but following accesses cause no page faults, so performance is good. Let's talk about possible live migration solutions generally. Two types of migration Pre-copy migration is when the virtual machine memory is migrated, while the virtual machine and the device is running on the source host. Now, since the device can modify the virtual machine memory, we need to detect that and update the copy and the destination. This can be done in a variety of ways. Patch faults will work, of course, or the device can report the changes pages to the host through some asynchronous interface, or the hypervisor can process the device rings for a duration of migration. Pre-copy I just described, that's when an access causes destination to fetch data from source hypervisor. Again, page faults do fix it, or it can be supported by running a software emulation until migration completes. So this can be potentially for a long time. There's an interesting issue when you deal with line migration with hardware devices. And that actually has to do with control plane of the device. So to move a VM, a virtual machine, between hosts, devices that it uses on both hosts needs to be compatible within themselves. But how can we ensure that when the devices are potentially from different vendors? Devices sold by different vendors differ significantly. They even differ for a single vendor. They can expose different optional capabilities such as offloads, amount of resources such as queues, interrupts, and so on. So the only hope seems to be to find the least common denominator supported by all hardware and use that to start a virtual machine. This looks like something that should be solvable with some tooling. For example, a tool could exist alongside QEMU, which can query and report the capabilities of host hardware devices. Now, this tool is run on each node, and it collects info about all the supported features, the number of resources such as Virtqueue, interrupts, and so on. After getting the information from all cluster nodes and collecting them together, another tool can then merge the reported information and come up with the least common denominator that can migrate across the cluster. So in an example on this slide, some features are only present in part of the cluster, and therefore after merging they are disabled. The number of Virtqueues also differs between nodes, so the least number of Virtqueues between all nodes is used. Now, starting a virtual machine with the specified parameters for the device can ensure that the device can be instantiated identically on all cluster nodes, so VM can be migrated between them at will. And the Virtio OTC is looking for even more optimization helpful for the hardware. One idea is to try and improve batching of use descriptor writes by the device. The issue we are trying to solve is that sometimes a single use descriptor refers to multiple available descriptors. So let's look at this example. Here, descriptor number 9 implied use of descriptors 8 and 7, for example, because of the in-order feature. And in that case, device writes out a single descriptor number 9 and then skips forward in the ring over 2 descriptors, since the use of 2 descriptors 8 and 7 was implied. So that's not the problem as such, it works. But this does mean that multiple write transactions are now necessary to write out the use descriptors, because there's space here between descriptors 9 and the following descriptor. Now, before we discuss the solution, let's just shortly talk about the reasons for skipping the descriptors like this. That's what's creating the problem. And this has to do with the rule that device must only use descriptors that driver has made available. And therefore, it must always stay behind the driver in the queuing. This way, each descriptor is first written by the driver and made available to the device. And then it's written by the device and marked as already used. However, if the driver is allowed to get ahead of the device by more than the full ring length, then it will start wrapping around and overwriting used descriptors that device just wrote. Skipping descriptors keep device and driver in sync, more or less, and not allowing the device to fall too far behind the driver. We are considering an alternative way for the device to write out used descriptors one after another without skipping space. To maintain the correctness invariant, device being behind the driver, the device can detect driver wraparound. That is that it processed the ring full worth of descriptors and skip to the beginning of the ring at that point. Take a look at an example. Here, device skipped 3 descriptors, 2, 5, and 8. After writing out descriptor 9, it detected that the end of the ring is 3 entries ahead. And it then skipped straight to the beginning of the ring, making sure the driver is not too far ahead of the device. Driver can also keep track of skipped descriptors. Alternatively, device can set a descriptor flag to signal driver to skip to the beginning. In this way, a single PCI Express write can signal use of multiple descriptors, potentially up to a full ring. So, to summarize, a large existing ecosystem makes Virtqueue a compelling option for new devices. We are always looking to enhance the way we handle hardware Virtqueue devices, with work on both performance and new features. And contribution is open to everyone, so please do join us. This ends the talk. If you have any questions, please feel free to reach out. The best way to do this is to post them on the Virtqueue mailing list, since it is preferable to have all discussion happen in the open. The address is on the slide. Thank you very much for your patience and have a good day.